Welcome all in this lecture of thermodynamics. In this lecture, I will discuss about some basic concepts of thermodynamics, and this discussion will be from the book of Garg, Ghosh and Bansal. So at first, let us learn what is thermodynamics. Thermodynamics deals with transformation of thermal energy into other forms of energy and vice versa. This subject evolved out of the search for an efficient engine during industrialization era in Europe. But today it finds wide applications in all facets of physical sciences and beyond, from combustion to power plants, refrigeration, and rocketry. Thus, thermodynamics has huge application in modern day. Even at home, we have several appliances or gadgets in which thermodynamic considerations play an important role. Like classical mechanics, thermodynamics is also based on empirical laws. What are empirical laws? Empirical laws means that there is no way to prove them and is therefore phenomenological. Nevertheless, it is very exact and powerful. That is, the laws of thermodynamics are very exact and powerful. Why? Because each of these laws introduces a new concept like temperature, internal energy, entropy. That is, from thermodynamical laws, we can have some concept about temperature, internal energy, entropy, etc., which gives a definite meaning to physically measurable quantities and provides useful correlation between observable properties of matter. For this, we need to develop a mathematical formulation of thermodynamics. So before the mathematical formulation, we should have we have to learn some concept about thermodynamic system, surroundings, and boundaries. So what is a thermodynamic system? A thermodynamic system refers to a certain portion of universe selected for investigation. It is imagined to be distinct and set apart from everything else. That is, we have to select some system which is set apart from everything else, and it is a certain portion of the universe. This means that a thermodynamic system is essentially macroscopic. It must be macroscopic one. Now, what are examples of thermodynamic system? In engineering, some important thermodynamic systems are gases such as helium or air. It may be vapor such as steam. It may be mixture such as air gasoline vapor or phenol water mixture, and vapor in contact with its liquid such as liquid ammonia and vaporized ammonia. So all these are examples of thermodynamic mixture which are important in engineering application. However, in physics, in addition to the aforesaid systems, we consider systems such as stretched wires, electrostatic capacitors, thermocouples, magnetic materials, surface films, electrical cells, etc. Obviously, a thermodynamic system will be perceptible to our senses. A system may be simple or it may be complex one. It may be homogeneous or heterogeneous. It will, however, always be finite. Now, what is homogeneous system or heterogeneous system? Suppose there is some gas in a cylinder and this cylinder is fitted with a frictionless leak-proof piston. So such system constitutes a simple homogeneous system. So in homogeneous system there is no mixture. whereas a phenol water mixture constitutes a more complicated heterogeneous system. So in heterogeneous system, there is some mixture where each component can exist in a different phase. So these are the difference between homogeneous system and heterogeneous system. Everything outside the system that can influence its behavior constitutes the surrounding. So what is surroundings? Surroundings is such thing that is outside the system, but it can influence the behavior of the system. And the envelope which encloses a system and separate it from its surroundings is called the boundary of the system. So let us look at this figure. If this is the system, so the envelope of the system will be its boundary, and beyond the boundary, that is surroundings. So this one is the system and this one is the boundary. The boundary of a system may be real, as in the case of a gas enclosed in a cylinder. Suppose there is some gas enclosed in a cylinder, so it has some real boundary, or the boundary may be imaginary. Suppose if we assume that some gas is flowing through a zigzag pipe, we are assuming that. So in that case, the boundary may be imaginary. However, their existence is important to visualize the system distinctly. The boundary of a system may or may not allow it to interact with its surroundings. And this concept, that is, whether it will allow or not allow to interact with its surroundings, depending on this concept, we can divide the boundary in different categories. For example, let us consider a boundary which prevents any exchange of energy and matter between the system and the surroundings is termed an isolating boundary. So what is isolating boundary? Isolating boundary is such a boundary that will prevent any exchange of energy and matter between the system and the surroundings. So for isolating boundary, the system is then said to be an isolated system. Why isolated? Because isolating boundary prevents the exchange of energy and matter between the system and the surroundings. So in that case, the system will be a isolated system. Such systems are not affected by their surroundings because it is isolated, and will not be of much interest from the thermodynamic viewpoint. However, if the surface of a system permits exchange of matter between the system and its surroundings, the system is said to be an open system. So for open system, the boundary permits the exchange of matter between the system and the surroundings. On the other hand, if exchange of energy only and no matter occurs, I am repeating that, if exchange of energy only and no matter occurs, then the system is said to be a closed system. However, the closed system is not an isolated system, because in isolated system there is no exchange of energy and matter, but in closed system exchange of energy occurs, but there is no exchange of matter. So this is the difference between a closed system and isolated system. The exchange of energy can take place either thermally or by doing work on a system. As in a closed system, there is some exchange of energy. So how the exchange of energy takes place? So exchange of energy takes place either thermally or by doing work on a system. For instance, heating a system belongs to the former category. That means that in this case, if you heat a system, then the energy can exchange via thermal process. That is thermal exchange of energy if you heat a system. However, if you compress a system, suppose there is some gas in a cylinder and you are compressing it, or you are applying some magnetization in some magnetic materials. In that case, there will be exchange of energy, but in this case, the exchange of energy takes place by doing work on a system. As we are compressing the system or we are applying some magnetization, that is, we are doing some work on a system. A surface which prevents thermal interaction is known as adiabatic, and the system is said to be thermally isolated. This is very important concept because we will discuss about this thing later on in details. So let us repeat the sentence again. A surface which prevents thermal interaction is known as adiabatic, and the system is said to be thermally isolated. On the other hand, if exchange of heat occurs through a boundary, it is called diathermic. So what is the difference between adiabatic and diathermic? In adiabatic system, it is preventing the thermal interaction. On the other hand, if the boundary is diathermic, then there is exchange of heat through the boundary. So depending upon the concept of heat exchange, we are dividing the boundary in adiabatic and diathermic. Obviously, a system with diathermic boundary will be in thermal contact with its surroundings as there is some heat exchange. So in case of diathermic boundary, there will be thermal contact with its surroundings. Now we will discuss that what is a state of a system and what are thermodynamic variables. To describe the motion of a mechanical system, we first write down its equation of motion and then solve it. So in mechanics, the equation of motion are familiar to us. We all know about the equation of motion. So what are equation of motion? If we solve some equation of motion, then what we get? We get some information about the time variation of the position vector associated with the system. So in mechanics, time and position, these two quantities are very important. The instantaneous state of a mechanical system is represented by its trajectory. So instantaneous state of a mechanical system can be represented by two variables, that is time and position. Because if we want to describe some trajectory, then you have to describe the time variation of the position vector. So in mechanics, this time and position are very important to describe the state of a mechanical system. Similarly, in thermodynamics, the state of a system at any instant represents its condition at that time. Again, I am repeating, that is the state of a system at any instant represents its condition at that time. It is specified by a set of experimentally measurable quantities called variables of state or thermodynamic variables, such as temperature, pressure, volume, electric field, surface area, etc. So if we want to describe the state of a thermodynamic variables, then we need some variables such as temperature, pressure, volume, electric field, surface area. So these variables are used to describe the state of a system at some instant. An equilibrium state is a particularly simple condition of a system in which variables characterizing it do not change with time and are reproducible. So I will describe about thermodynamical equilibrium in details later, but right now, what do you mean by equilibrium? An equilibrium state is a particularly simple condition of a system in which variables characterizing it do not change. Again, I am repeating, that is, variables characterizing it do not change with time and are reproducible. So this is known as the equilibrium state. Thermodynamic variables may be divided into two categories: intensive variable and extensive variable. Let y be a macroscopic parameter specifying the state of a homogeneous system. Suppose that the system is divided into two parts, say by introducing a partition. Suppose there is some particular box containing some gas, and we are dividing the box in two parts by introducing a partition. Let y1 and y2 be the values of this parameter for two subsystems. That is, after the partition there are two subsystems. So y1 and y2 be the values of this parameter for two subsystems. Then y is said to be extensive if y equal to y1 plus y2, and y is intensive if y equal to y1 equal to y2. These are the difference between intensive variable and extensive variable, and we have explained it mathematically. So in physically, those variables of a system in a given state that are independent of its mass or the number of particles are called intensive variables. So this is the physical description of the intensive variables, those variables of a system in a given state that are independent of its mass or the number of particles are called intensive variables. So intensive variables are independent of its mass or the number of particles. We know that pressure, surface tension, electric field, temperature, these are some intensive parameters. If small f and small g are arbitrary intensive variables, then f into g or f by g or del f by del g and f plus g will also be intensive variables. So if f and g are intensive variables, multiplication of f and g, division of f and g, differentiation of f with respect to g, and summation of f and g all are intensive variables. Now, what are extensive variables? The variables that are proportional to the mass and to the number of particles in the system belong to the category of extensive variables. Those variables that are proportional to the mass and to the number of particles in the system belong to the category of extensive variables. What are the examples of extensive variables? Extensive variables are volume, magnetic dipole moment, charge, area, length, electric dipole moment, etc. If capital F and capital G are two arbitrary extensive variables, then F plus G will be an extensive variable. If we add them, it will also give an extensive variable. However, F by G and del F by del G will be intensive. But if you divide F and G or differentiate F with respect to G, then it will give you intensive variable. Similarly, we find that if small f is an intensive variable, and capital F is an extensive variable, then small f into capital F by small f, and del f by del f, that is differentiation of capital F with respect to small f, will be an extensive variable. So these are the mathematical properties of the intensive variable and extensive variables. And we have already discussed about the examples, that is pressure, flux density, potential difference, surface tension, electric field. Those are intensive variable, whereas volume, magnetic dipole moment, charge, area, length, electric dipole moment, all these are extensive variable. Now I will discuss about thermodynamic equilibrium. The state of a system undergoes a change when it invokes work-like and or thermal interaction with its surrounding. So when there is some thermal interaction of a system with its surroundings, the state of the system undergoes a change. After a period of time, a state is reached when all observable changes in its measurable properties cease to occur as long as external conditions remain unaltered. So after a period of time, a state is reached when all observable changes in its measurable properties cease to occur. Cease to occur means that is that change which occurred earlier, that change ceased to occur. This state is known as equilibrium state of the combined configuration, and the system is said to be thermodynamic equilibrium. So in thermodynamical equilibrium, the changes in the variable cease to occur. That is, there is no change in the thermodynamic variables. Since a thermodynamic system may be hydrostatic, may be physical, may be mechanical, may be chemical, so we define thermodynamic equilibrium as the state achieved by a system when it is in mechanical, thermal, and chemical equilibrium with its surroundings. So thermodynamical equilibrium is a generalization. It considers mechanical equilibrium, thermal equilibrium, as well as chemical equilibrium with the surroundings. We define mechanical equilibrium as the state of a system in which it experiences no pressure or elastic stresses and there is no unbalanced force between the system and its surrounding. Suppose a gas in a cylinder fitted with a piston is said to be in mechanical equilibrium if there is no unbalanced force on the piston. However, if pressure is not uniform throughout the system, turbulent motion, expansion or contraction will be produced. To understand the concept of thermodynamic equilibrium further, let us consider two systems in thermal contact through a diathermic wall. So you consider two systems which are in thermal contact through a diathermic wall. One observes that changes occur in their properties such as volume and pressure. So volume and pressure of the two systems will change on thermal contact. Soon these changes cease and the two systems are said to be in thermal equilibrium. That is, after some time, these changes cease to occur. That is, there is no change in the thermodynamic variables such as volume and pressure. So that uh, at that time or at that instance, we will say that the two systems are in thermal equilibrium. One can therefore define thermal equilibrium as the state attained by two systems placed in thermal contact through a diathermic wall. If a hot body is dropped into a liquid in a calorimeter, after some time the calorimeter and its contents attain an intermediate temperature. We all know about this concept. So at that time, the system is then said to be in thermal equilibrium. So this is one example of how thermal equilibrium occurs. If a system such that it neither shows a tendency to undergo a spontaneous change in its internal structure, such as during a chemical reaction. So, if a system is such that it neither shows a tendency to undergo a spontaneous change in its internal structure, nor allows transfer of matter from one portion of it to another, such as by diffusion, it is said to be in chemical equilibrium. So, when the system is in chemical equilibrium, so at that time there is no transfer of matter, that is, there is no diffusion and there is no change in its internal structure. So, that condition is known as the chemical equilibrium. So, thermodynamical equilibrium actually means that it is in mechanical equilibrium, chemical equilibrium, as well as in thermal equilibrium. So, all this we have discussed in this lecture. To understand these concepts more clearly, I advise to go through the textbook of Garg, Bansal and Ghosh, Thermal Physics with Kinetic Theory, Thermodynamics and Statistical Mechanics. And thank you all to who have listened this lecture.